Hi everyone, my name is Ali Arsanjani. I'm a worldwide tech leader and chief principal architect with Amazon Web Services. And along with me is Samir Joshi, machine learning engineer for Qualtrics. I'm going to be talking to you about how to use SageMaker to develop ML models faster, featuring Qualtrics. Initially, we're going to be talking about the ML lifecycle for enterprise scale ML, some of the old and new features. Then we're going to talk about experimental and automated machine learning sections of the lifecycle. Then we're going to go diving deep into the music recommendation example, which is an end-to-end example. The factors for accelerating ML maturity and adoption are then going to be discussed, and then we're going to go into the use case exploration with Qualtrics. And then we'll have a Q&A if necessary. Initially, the ML lifecycle, which you all probably know very well, had the data prep, train and tune, and deploy and monitor parts of the lifecycle. And the industry has been adamant about augmenting this with additional capabilities. These capabilities were provided to us last reInvent by AWS. These include things like data wrangling, feature engineering, creating end-to-end pipelines for automated workflows, having the ability to govern your data artifacts, code artifacts, and model artifacts, and thus understand the lineage between them, deposit your models in a model registry and have control and governance over them, and to understand and detect bias, pre-training, post-training, and at model inference time, and also be able to interpret why a machine learning algorithm provides you with some kind of a prediction. So with these features, we have a ML reference architecture for Amazon SageMaker. And in this ML reference architecture, you can see all the components that are currently necessary in order to take you through your end-to-end lifecycle in machine learning. In the early stages, you want to wrangle your data, clean your data up, define transformations, send them off to be processed, deposit them in a feature store, train and debug your models, assess bias in your data set, mitigate that bias, assess bias in your models that may have occurred, mitigate those. And then once the model is acceptable from both a metrics and a bias perspective, deposit them in a model registry. Subsequently, you can pick that model up and deploy it in a variety of ways. In this case, we're going to be using real-time endpoints that SageMaker provides. We can also provide the batch transform capabilities, which allows you to batch data up, or the async capabilities that provide us with the ability to handle longer running inferences. And then finally, we have monitor capabilities with SageMaker Monitor in order to monitor the endpoints to detect data drift or concept drift, and then re-trigger the pipelines so that we can automate the process over again with new data and building new models as necessary. The other necessary ingredient for ML Ops is the ability to integrate with CI/CD pipelines, continuous integration, continuous development pipelines, where you change your code and you want them to go into production in a seamless fashion. So let's look at an end-to-end example in which we will be looking at the music recommendation example that we have in our AWS SageMaker examples repository. In this section, we will be seeing the first part of the notebooks that we have corresponding to this example. And I'm actually going to be switching over to the notebook here. And as you can see in the notebook here, we have about 10 notebooks in this Jupyter Lab environment, which is SageMaker Studio. So SageMaker Studio is pretty much a single pane of glass with a Jupyter Lab interface that allows you to tap into all the different varieties of elements that SageMaker gives you. For example, you can tap into projects, you can tap into feature stores, pipelines, experiments, model registry, etc., etc. See your endpoints and look at Data Wrangler. For now, we're going to go one by one through each of the notebooks and just highlight the salient points about the notebook. We're not going to be walking through every single detail in the notebook. So with that, I'm going to come back to the actual PowerPoint again. In the first notebook, we're going to be looking at early phases of the data science and machine learning lifecycle, where we're doing exploratory data science. We have 3 data sets that are synthetically generated data sets. One pertains to music tracks, and the second, the users and their preferences. And the third are the 5-star ratings that different users have given these tracks based on their instrumentalness, acousticness, and a variety of other characteristics. We're going to be using the Data Wrangler capability within SageMaker Studio to define transformations that can then be leveraged for your purposes of transforming the data into additional formats that you would need for feature store and model training. So in the first notebook, which is notebook number 0, we give an overview of the architecture and the data. Here is some sample of the data. In this case, we're taking a look at the tracks data set. As you can see, we have the length of the music, the length of the track, its energy, acousticness, valence, speechiness, instrumentalness, etc. These are all being assessed, and they will be used in the recommender system. Next, we're going to load that into Data Wrangler, and we're going to define transformations for SageMaker processing in order to do some transformations that we have defined so that we can prepare the data for the feature store, which will then be utilized for training. SageMaker Data Wrangler inside of SageMaker Studio allows you to define a variety of transformations. You have multiple input sources like Amazon S3, Amazon Redshift, other connectors are existing connecting you to Snowflake, and there are other connectors planned. These connectors will load your data, which is a subset of the data that you have, and that subset will then be visually utilized to define transformations. And these transformations are a variety of different things such as vectorizations, deleting null values, cleaning up your data, and getting it ready so that you can have a single gold source of truth for training. So in that data prep capability, we're going to be leveraging Data Wrangler, and the transformations are being defined so that we can pass on these transformations to SageMaker processing. And we're going to soon talk about what SageMaker processing does. It will take these transformations and it will apply them to your entire data set. Let's say you have petabytes of data. And these data sets are then going to be ready to be deposited in an offline feature store so that then we can start training. So if we go to the next notebook, which is 02A, and notebooks 02 consist of 3 A, B, and C notebooks. One is for tracks, the 5-star ratings, and the users. So we're going to be looking at one of the salient features here, which is to create a feature group. Inside of SageMaker Feature Store, we have the notion of a feature group. It's a collection of features. Think of it almost as a database table. Although remember that Feature Store is not a relational database and should not be used as a relational database. So what we need to do is create a feature group and provide the information so that a feature group is created inside a feature store and then ingest the feature store components into it. In order to do so, we will basically define what the input dataset sources are for the processing job that is going to be processing the input features and depositing them into the feature store. So here in this, any of the notebooks 2A, B, and C, we're going to be defining the processing input and the processing output, which is going to be the feature store. From inside of SageMaker Data Wrangler, inside of Studio, you can actually select different output sources, or destinations rather. One is the feature store, another is pipelines, and another is just a script. Then Data Wrangler will automatically generate a Python notebook for you. And in that notebook, in this very low code notebook, meaning you don't have to write much code, all of the code is actually generated for you. It will actually define to SageMaker Processing what kind of transformations have to happen to your data and where they should be deposited. Here we're showing where the output destination of the processing job, the SageMaker Processing job, should be defined. And in this case, it's going to be the offline feature store. If we take a look at the feature store from inside of SageMaker Studio, this is what it might look like. So we would basically click on that drop-down box, select feature store, and we can get a variety of different characteristics of the feature store, including a feature group summary, its definitions, what are the actual definitions of the actual fields and features, and any kind of sample queries we would like to define. With SageMaker Feature Store, you can basically build these features once, meaning transform the raw data into a format that is now ready for machine learning, and deposit that inside your feature store as a gold standard so that you can transform these features once and then reuse them again and again across different teams, different projects to train different models in your organization. There may be common data sets that could be used across different models and different projects. And you won't have to go back every time and be unsure as to what transformations were applied, whether these transformations are now ready for machine learning or not. So it provides a significant amount of governance. Feature groups are discoverable by search. They're reproducible feature transformations that have been defined. And you can extract accurate training set data sets from them. There are low latency lookups for inference time from the online feature store. And there's a consistency between the offline and online feature store, which makes it consistent for training and inference. So the feature store allows batch and streaming ingestion of data. So you have high throughput writes for ingesting features. You have online and offline features for real-time prediction with your online features, and offline predictions, offline features for historical data and batch predictions. There is metadata and data cataloging that can be done by storing the metadata for the features and leveraging automatic data cataloging and a very easy query interface using Amazon Athena into the actual data store. You can discover the features and search them, and you have, as always within AWS, highly secure access control, not only with the IAM capabilities, but also with VPCs and private link. And everything is fully managed. So you can look at this example where we can discover the feature groups by name, by description, by tags, or other metadata. You can manage different features using different feature groups and collect them in these feature group collections, configure them for online and or offline storage, and create data catalogs for each of the feature groups. This all includes a comprehensive set of metadata that you can add as feature group tags. If we put the feature store in context, you can have streaming input using Kinesis or other streaming input capabilities, such as Kafka, and you can have batch sources as well. They will all go to the online portion of the SageMaker feature store, and you can then replicate them automatically to the offline feature store. You can either use them directly in the online feature store for inference, or there's a less than 15-minute replication time frame that will happen between the online and offline feature store, where in the offline feature store, they're available for model training and batch scoring. SageMaker processing allows you to spin up a cluster automatically in a completely hosted way using your favorite frameworks such as scikit-learn and Spark, or you can bring your own container, do all your processing of your data, and then deposit it where you need it, where you point the output, in this case, feature stores. So in order to do so, here's an example. We set up the processing by defining a processor, and then underneath it, we create a processing job. And with that processing job, we can kick it off, and when it's done, it will point to the output, which is the actual feature store. So with that, we've now prepared all our data sets, put them in a feature store after processing them with Amazon SageMaker processing. Now what we're going to be doing is training a model, defining what lineage, what correspondence there is between the code, the data, and the model, and then possibly tune it if necessary. We could use Amazon Clarifai to detect bias in the data or bias in the model, and then pick, after we mitigate the bias, we can pick the best model and deposit it in the model registry. So this is what the next notebook is going to show us. This is notebook number 3, which is train the model, provide lineage, deposit in the registry, and by the way, we're also going to be looking at how we debug. So in terms of lineage, there are 3 kinds of lineage. We would initially start by creating an artifact. And this artifact, in this case, is a data artifact. Where did this data come from? There is a model artifact, which talks about the trained model and where we trained the model and what algorithms we used in order to train the model. We then associate these artifacts together, and then they're ready to be deposited in the actual model registry. If we take a look at what we've published in what we call the ML Lens, we have a well-architected framework at AWS, and there's a very specific lens that we have on machine learning. So there's a well-architected lens that we've published, and this is a snippet from that section, which defines the best practices here for our end-to-end architecture. In this case, we're taking a look at the training and tuning, where we have features, how we build code, select the algorithms, train and debug the models, establish lineage, possibly tune them, and then deposit them in a registry. We can list the artifacts here as shown in the bottom. Okay, now what we're going to be doing is we're actually going to get data from the offline feature store that has been concluded after SageMaker processing deposited all those transformations we defined in Data Wrangler into the feature store. So in order to get the data, we simply form a SQL statement, such as what is depicted here in the select statement, and we form an Athena query. Athena gives us the ability to run SQL over AWS S3. And we get the result back as a data frame and put it in a table. As part of training, what we're going to be doing initially is we're going to be getting data from the feature store. In order to do so, we're going to formulate an Athena query in SQL, and we will execute that query and get the results back into a data frame as depicted here. So in the next phase of training, we would like to remind you that there are different kinds of algorithms that we provide with Amazon SageMaker. These include anything from k-means clustering to XGBoost to different PCA, LDA. All of these different kinds of normal machine learning algorithms are there as standard containers. We also support all the different major frameworks, including scikit-learn, PyTorch, TensorFlow, MXNet Chainer, and XGBoost containers. Or you can bring your own container for training. And what SageMaker does is spins up a cluster, trains your model, and then tears your cluster down as necessary. In order for us to support debugging, we will add a hook into the estimator for the XGBoost estimator. And this allows SageMaker Debugger to actually provide a configuration definition that will then pull out all the information that has been deposited by the training job in a particular location. And it will look that up, and in this particular case, it will look for metrics, it will look for feature importance, Shapley values of different sorts, full and average. And at the very end, you can see the fact that we have rules that we can define. In this case, the rule that we're defining is loss not decreasing. So what this is if you have multiple epochs that you're training on, and you see that the loss is not decreasing over the epochs, the training will stop. So these rules are part of your hook into Amazon Debugger, which will then be integrated into your estimator. So as you know, in order to train a model, we create an estimator. In this case, we're using an XGBoost estimator to give us a ranking that we will then provide as a curated playlist of music for the recommender system. So in Amazon SageMaker Debugger, we have spun up a different process that is going to be looking into your training process. This is all hosted, and it will capture the relevant data you have defined. It will do some data analysis and debugging, and you can define rules for automatic error detection, such as the loss not decreasing. You can also get different alerts, and you can visually analyze the debugging that has been happening. Ultimately, the debugger can visualize the results as follows, as you can see below, and provide you with a variety of statistics that will help you debug the training part of your machine learning process. In this case, some of these elements that we've looked at are providing us with the different iterations and the different root mean square error between training and validation, which we have specified as metrics in the debugger hook during the training. We've also specified various Shapley values, which indicate the importance, the relative importance of various features for our model. In this case, we can see that the energy 5-star rating, liveliness, energy, and tempo are the top 4 that have been identified by the debugger. And these are additional reports that the debugger can provide you with in order to help you debug your training program. Okay, once we've trained our models and deposited them in the model registry, along with the lineage artifacts that accompany them, we can then pick a model, deploy the model, and serve the model, run inference on it. And we can run inference on it, giving it data using the online feature store with a very simple get record. You can also get multiple records at a time. SageMaker Hosting provides you with the ability to spin up a very scalable cluster of endpoints. And whether you bring your own container, use the frameworks that we provide, the algorithms that we provide, or the marketplace containers, it can all be accessed through an HTTPS endpoint from a client application, and it resides in a VPC for full security. So for the deployment to happen, we take the estimator and call a .deploy function, which is part of the SageMaker software development kit. And we specify the size of the cluster, the number of virtual machines, and the actual endpoint name, and where the model resides. The model that has just been trained and was deposited in the model registry. Typically, it generates a model.tar.gz file, a zipped file that you can then point to here and will be deposited, essentially spun up in a cluster that you define. In this case, it's a cluster of 1 with an M4X large that we deploy to. So we can do 3 things. 1, we can have real-time inference, where then you can do A/B testing. You can direct some of your traffic to that particular model, let's say 95% of your traffic, another 5% to a new model that you're testing out. And these are all capable of being integrated with VPC Private Link, and you can invoke the endpoints and understand the resource usages using standard APIs. The other way we can do so is through batch inference, where your model is launched on demand with an input data in S3. Large amounts of data, very typically, are best for batch inference. And what we then do is deposit the results back in the S3 bucket. So it's not a S3, it's not a API request. It's more of a, here's your data in S3, run the inferences for a lot of data, and then transfer them back into an S3 bucket. And your app can pick them up, put them in a database. There's a third mechanism that we've provided recently called SageMaker Async, which is in between the two. This is typically used for large language models that take a long time to perform predictions or inference by their very nature. And so it's somewhere between real-time and batch, but we provide them kind of a threshold so that they don't time out. And another step we can discuss here is how do we fine-tune the model, or rather, how do we tune the model as in hyperparameter optimization? So we can take a look at the space that has been created. We can do a grid search to search that space, or we can do a more intelligent search using a Bayesian search, which provides Bayesian optimization strategies to reduce the search space and essentially find the best performing models with the different parameters that have been tried in your hyperparameter optimization jobs. You end up with the best model to deploy. Beyond that, what we'd like to do is, once we have actually deployed the model, we need to obviously run inference on it, or run predictions on it, so to speak. To do that, we create a predictor. And let's say for a given sample user, in this case 11005, we are going to perform the get record function on the real-time feature store, on the online feature store, and we're going to get some responses back. And we're going to store those responses somewhere. And if we take a look at those responses, here is your curated music list. Now, these are hashed so that for copyright reasons, we're not showing the actual track names or references to the actual music, but these would be, you can look these up essentially using these hashes to get to the actual music tracks, which would be recommended for you and specialized for that particular user, so to speak. Finally, in order to do some AI explainability and understand which features were most influential in running your inference, we can use Amazon Clarifai in order to do this. And this is post inference, and it will give you a report which will explain the model predictions by showing which of the features had the highest propensity to influence the model. And in this case, we see that the energy 5-star, instrumentalness, the genre of the music, R&B, seem to be, and the genre of country seem to be the top 4 that are influential in providing predictions. And that's why probably those that particular user will be finding them more in their playlist. Now, we've deployed a model into production. We have to monitor that model. So there needs to be automatic data collection of that endpoint, continuously monitored on a given schedule, and basically having the flexibility to rewrite rules in order to define what conditions should be there if the model has concept drift, and that we should be notified, or what action should be taken using maybe a CloudWatch event engine alert. Or some visual data analysis can be done in a graph format. In order to do so, we will use SageMaker Model Monitor. In SageMaker Model Monitor, after we actually train the model in SageMaker and deploy the endpoint, we can baseline the model, which means we will identify the levels of accuracy, precision, recall, etc., that are important for us. So we know what we're starting from. And then as the model evolves over time and predictions are made, if the model starts drifting from that level of accuracy, we can define rules which say if it goes within a certain threshold of departure from that level of accuracy, we actually have to inform someone through a CloudWatch alert. So we then can set up a schedule of monitoring these models, let's say on a daily basis, and collect all of these inference requests, collect all the metrics, analyze them, and if necessary, create a CloudWatch alert in order to take action. So let's see how this happens in brief. In the 5th notebook, you can see this in detail. There are 3 sections to it: enabling capture, baselining, and enabling continuous monitoring. We do the first one for enabling capture by creating a data capture configuration. And the subsequent step is to baseline the model by creating a default model monitor, which will allow us to monitor the baseline of the actual model that has been deployed. Subsequent to that, we're going to define a schedule. So we're going to use the create monitoring schedule on the monitor object, and we'll give it some baseline statistics, all the suggested constraints, and we're going to set this up as a cron job for a daily monitoring of that particular endpoint, the SageMaker hosted endpoint. When something happens, it will trigger an alert as necessary. And we can explore some of the generated statistics that are ensuing as a result of the monitoring of the model. So using SageMaker Model Monitor, we can identify model drift, data drift, and take action as necessary. You can see them in a graphical format, and you can modify the different parameters of the graph to give you a visual representation of what is transpiring. Now, all of what we did, we have done pretty much in the exploratory phases of data science. Now, how about automating this as a workflow so we don't have to do everything manually, so to speak? We've done all the data wrangling, we've defined the transformations, done the training, deployed the model, but we want to do this on an automatic scheduled basis. So SageMaker Pipelines gives you the ability to create automated workflows for MLOps. We also have other mechanisms like step functions and Apache Airflow, managed Airflow, that we can provide you with. SageMaker Pipelines provides you with very specialized granular level control over this lifecycle. Now let's take a quick look at how that happens. So with pipelines, you can access this whole orchestration process with a Python SDK that you can build in with your workflows. It manages your workflow executions just as SageMaker manages your training jobs or can host your endpoints. It allows you to catalog the different versions in the model registry of the SageMaker pipelines that you have executed. And it gives you a fully managed MLOps capability that can integrate with CI/CD so that you can do continuous integration and deployment. As we discussed earlier, in the model registry piece, we have end-to-end lineage tracking for governance and audits. where the data, the code, the metrics, and the model artifacts reside through the pipeline. So on Notebook 6, the pipeline notebook, we have several steps, such as basically all the steps we've taken so far: wrangling the data, pre-processing steps, doing the train test split, training the model on an XGBoost model, deploying the model, registering it in the model registry, and then deploying it and then monitoring that endpoint, combining the results, and running inference. So I'm going to skip to the last step, because you can see how easy it is to combine these steps that you define into a SageMaker pipelines in a list in Python. And basically, each one of these is a processing step. And each of the processing step allows you to actually combine them together in a pipeline. So for example, here we can take all of the input that we get from different sources of tracks, ratings, and user preferences and combine them together into the earlier part of the pipeline and define a source for the pipeline to start processing. There are other steps that are non-generic processing steps that are specialized steps, such as training steps or tuning steps that are depicted here. In the training step, we specify what the inputs are for training, where the estimator should be, and we allow the actual step in the pipeline to initiate the training using the estimator that we just defined above. So each of these are essentially happening automatically as a node in a directed acyclical graph that you can define with SageMaker pipelines. So with that kind of brings us all the way around back to our reference architecture with SageMaker to help you run your machine learning workloads across the lifecycle. Now, organizations go through a variety of trials and tribulations and growth pains in order to get from one level of maturity to another. They start exploring things, and then you can consider it to be of a crawl, walk, run, and sprint set of essentially maturity levels. And as you go from the explore to the crawl to walk to run to sprint, you're increasing your sophistication over time. And the organization's capabilities, the return on investment for the business, the technical prowess increases over time. And for doing that, you also essentially need to be aware of the 5 pillars of a well-architected framework. These include operational excellence, security, reliability, performance efficiency, and cost optimization. Now, if you take those 5 phases of maturity, explore, crawl, walk, run, sprint, and you can see that in explore, those 5 pillars only need to be filled out just a bit. When you're doing the crawl phase, how much of these pillars do I need? Well, maybe I don't need to be super secure because I'm not exposing it to anyone. It's internal. Or maybe the reliability doesn't need to be 100% or close to that. So you may need less of these 5 pillars. And that's what's depicted here in this slide, which is how much of it is filled in each of these phases. Now, but as you get to the run and the sprint phases, you really need the combination of all of these important aspects of scalability, of cost optimization, of reliability, of operational excellence, so that you can scale and automatically scale in many cases and not worry about whether your system is going to go down. And you have to do this in different environments, in the development and test environment, in the staging environment, and in the production environment. As you walk through the different phases of maturity from explore to sprint, you have to do these across multiple environments, such as development and test, staging and production. Now, in each of these phases of maturity, you may need some aspects of the pillars of the well-architected framework. As you go up the maturity curve, you need more of it. But also, as you go up the environment maturity, which is as you move into production, you would need more operational excellence, more security, more reliability at the utmost. This is where the best practices on the left-hand side, depicted by that end-to-end reference architecture, comes into play. So the more of that you include in your maturity, and as you adopt more, the maturity level increases and the pillars of the well-architected program are better infused into your environments so that your production environments scale, are secure, are reliable, are performing efficiently, and are optimized for cost. Now with that, I'm going to invite my friend and colleague from Qualtrics to discuss their journey of using the AWS SageMaker platform and how they accelerated and went into more and more sophisticated levels of maturity with machine learning.
Thanks, Ali. Hi, my name is Samir Joshi, and I'm a machine learning engineer at Qualtrics, currently working on our IQ research and development team. Here, I focus on building production-ready ML systems, as well as building the Qualtrics ML platform, powered by Amazon SageMaker. Today, I'm here to discuss the ML journey for Qualtrics, how we got there, how we leverage SageMaker, and where we're headed next. Here at Qualtrics, we work on experience management, building technology that helps close experience gaps for customers, employees, brands, and products. We do this through the XMOS, the Experience Operating System. In this system, we identify gaps, know where to focus and what to do, and ultimately help build a culture of action. In order to do this, currently we have a few ML use cases, including natural language processing, predictive models with tabular datasets, and time series prediction, as well as many more that are in the works. Currently, Qualtrics is using large-scale machine learning for NLP at the scale of hundreds of millions of predictions to provide actionable insights that empower customers to better manage their experiences. With tabular datasets, we are building customer-specific models for churn predictions, classifications, and more that are unique to specific brands and their data. Additionally, with time series predictions and anomaly detection, we're able to identify gaps early and predict patterns for our customers. To do this, we leverage AWS SageMaker, and Qualtrics has standardized its labeling, data prep, training, and deployment processes using the Qualtrics ML platform, built on top of AWS Amazon SageMaker. To do so, we leverage SageMaker purpose-built tools such as ground truth, real-time inference, batch transform, and many more. In terms of the challenges we faced as we began this journey, we've grouped these into universal models and customer-specific models. For universal models, scaling large, deep neural network models that are dependent on GPUs, such as many of the language models used for NLP today, was prohibitively challenging and expensive in the Qualtrics infrastructure, which is a hybrid cloud environment split between the Qualtrics co-located infrastructure and AWS. Additionally, we had fragmented ML tools and processes that slowed down innovation, as there was not a secure, highly available notebook environment from which to conduct data exploration, analysis, and training on an on-demand basis. Finally, we lacked out-of-the-box labeling tools that would allow our data to sit in the same environment in which it was being labeled in, while being flexibly labeled at scale. On the customer-specific side, we needed workflows that could guarantee customer isolation at each step of the ML lifecycle, as customers want to be confident that their models built on their data are unique to them and don't share data or resources with other models. Additionally, given that models are customer-specific, we have a large order of models, in the tens, hundreds, even thousands going forwards, in which to deploy, and that these models are invoked with widely different load patterns, as every customer is different and accesses their models and predictions differently. This brings us to the Qualtrics journey for ML maturity. Like most companies, we've gone through the crawl, walk, and run phases, which we're currently in, and are looking ahead to the sprint phase for many of our ML systems. But we'll begin with the crawl. So in the crawl state, we ran a smaller selection of smaller models on production CPU instances inside the Qualtrics co-located infrastructure. Here, we had two major challenges. First, scalability, and second, time to launch. In terms of scalability, we lacked GPU or accelerator instances that would provide the throughput that we required, and this also prevented us from deploying larger, higher quality models for predictions. In terms of time to launch, we lacked a secure environment for data exploration and on-demand training, which slowed our ability to develop models and to productionize them. This really brought us to the walk phase, in which we deployed our first set of models on AWS SageMaker. And we used data and analysis, or we performed our data analysis and training in SageMaker using SageMaker notebooks, training jobs, and hyperparameter optimization, and ultimately built and deployed these models with SageMaker real-time inference on auto-scaling GPUs. Additionally, we used an experimentation platform in order to better track model metrics, benchmark models against each other, and ultimately sign off on models for production. In the walk phase, specifically focusing on how we leverage SageMaker, SageMaker Notebooks and SageMaker Studio have become our go-to environment as the scientist workbench. Additionally, SageMaker Ground Truth has allowed us to efficiently label data, while, and most importantly, leaving it in the same environment in which it was being stored. Additionally, auto-scale GPU instances through managed endpoints greatly reduced our time to launch and allowed us to achieve the necessary throughput for our customers. Moving into 2021 and earlier this year, we achieved the run phase for a large set of our ML systems, in which we have automated models that are created and deployed through pipelines for creating models, SageMaker training, and hyperparameter optimization, validating and verifying model quality through the experimentation platform, and ultimately deploying these models at production scale. These models vary in size from the smaller customer-specific models to the larger models that are universal and serve all of our customers. Currently, we are deploying between 10 and 50 models, and we continue to scale into the hundreds and thousands in the near future. For our universal models, we are currently deploying a variety of large-scale transformer-based models in production. For an approximate estimation of size, it's about 700 megabytes when all compressed and zipped together. We've run these both for real-time inference in low latency situations and batch transform when maximum throughput is required. And using SageMaker, we're able to deploy both of these with the same code base. Additionally, we've developed feedback pipelines for model monitoring and model retraining in order to continually improve our models for our customers. In terms of leveraging SageMaker, SageMaker has really allowed us to horizontally scale across all of our models and the new use cases that we're developing, specifically in terms of its ability for on-demand hyperparameter optimization, training jobs, and batch transformations, as well as real-time inference for hundreds of independent models. Looking ahead, we look at the sprint phase and how we can leverage SageMaker to achieve it. This includes functionality such as model versioning, data versioning, A/B testing, and configurable dial-up from rolling out models, feature stores, data processing pipelines, model CI/CD that joins in with our code CI/CD, and continue to tackle new use cases as we horizontally scale. As we go through this journey, the question was, why SageMaker? As we were evaluating at the beginning of last year, we found SageMaker to encompass all aspects of the ML lifecycle and continue to find that to be true today, as well as being highly integrated into AWS so that we can leverage other AWS functionality. It's highly available and scalable, and continues to be feature-rich as it releases new features that serve our use cases. And I'd be remiss to say that the partnership and commitment from the AWS team wasn't essential in our integration with SageMaker. In conclusion, the key takeaways here are really how SageMaker allowed us to deploy a set of models and to scale in a way that we couldn't do otherwise. With auto-scaling GPUs that allowed us 10 times the throughput with larger models than we'd ever deployed before, noticeably increasing productivity by reducing the time to launch for both ML engineers and applied scientists, and a significant reduction in infrastructure management, allowing both scientists and engineers to focus on building and deploying high-quality models for our customers instead of managing the infrastructure. I'd love to answer your questions, but for now, I'll turn you back over to Ali.
Thank you, everyone, for listening today. As Samir just discussed, the journey of increasing maturity in machine learning involves increasing sophistication as you move in these different phases and as you move through these different environments of dev, staging, and production. And we talked about how SageMaker as a platform allows you to go through these stages and provides you with all those tiers of the pillars of the well-architected framework and to be able to increase your maturity across the ML lifecycle.